Bismillahirrahmanirrahim. Alright class, Assalamu alaikum and welcome to the second lecture of week 4, and I will start off exactly from where we left. We have discussed the spherical coordinate system so far. We have discussed the fundamental shapes. We have discussed the curves formed at the intersection of a pair of fundamental shapes. These curves, okay, and we have also discussed the point which is formed by intersection of all the three fundamental shapes, okay, cone, sphere and radial plane. Not only that, we had also discussed in the previous class that if we are given with any of the two curves, latitude longitude or longitude radial line or latitude radial line, any two curves are sufficient to locate a point. But as we said that we always discuss any shape other than fundamental shape in terms of the fundamental shapes. So in 3 dimensions, the fundamental shape is of 2 dimension, that is surfaces are equals to constant, theta equals to constant, phi equals to constant. Therefore we must define all the curves, 1-dimensional curves or 0th dimensional point, in terms of the fundamental shapes, 2-dimensional shapes. Then we discussed the primitive unit vectors of spherical coordinate system, and we defined 3 for each of the fundamental shape. And then since we know that each unit vector is perpendicular to its respective fundamental shape, and we also discussed that at the point of intersection in 3-dimensional spherical coordinate system, at any point the 3 primitive unit vectors are perpendicular to each other. Since these 3 primitive unit vectors are perpendicular to each other and these primitive unit vectors are perpendicular to their respective fundamental surfaces, so indirectly we can say that at the point of intersection all the 3 fundamental shapes are perpendicular to each other at any point within the 3-dimensional vector space, 3-dimensional space defined in spherical coordinate system. And the same has been discussed in cylindrical coordinate system and the rectangular coordinate system. All right, so after that we have to discuss the differential volume, differential surfaces and differential lengths, and we are taking the same scenario which we took while discussing these topics, these differential entities in cylindrical and rectangular coordinate or Cartesian coordinate system. So we are taking the same scenario that this point is P mentioned here, the coordinates, example coordinates are mentioned here, this point is Q and this example coordinates are mentioned here. For P the coordinates are 3, 50 degrees, 30 degrees. For Q the coordinates are 5, 70 degrees and 60 degrees. So we are initially at this point P, so you can imagine that we are on a sphere whose radius is 3. And if we are at this point Q, then it means that we are on a sphere whose coordinates, whose radius is, we are on a sphere whose radius is 5. So obviously both the spheres are centered at origin, meaning that point Q is on some outer sphere as compared to point P, which is on some inner sphere. Both the spheres are concentric, obviously, because the radius of the sphere is always measured from the origin, which we have defined it so. Okay. Secondly, obviously, this point P is lying on a cone, which is making an angle 50 with respect to z-axis, and point Q is on a cone which is making a wider angle with respect to z-axis. So it means that if, let's say, this is the angle 50 with respect to z-axis, so this angle would be for example, this angle would be 70. It means that point Q is on some wider cone as compared to point P. Point Q is on some wider cone, 20 degrees wider as compared to point P. It means that this is wider cone, okay, and this is uh, this is a less narrower cone, so obviously we should expect that point Q would lie somewhat, you know, on the lower horizontal z plane as compared to point Q, but we cannot be so sure. Why? Because they point P and point Q are not on the same sphere. Had they been on the same sphere, we would have been dead sure that point Q is lying lower as compared to point P. But since, you know, the radius is changing, so we cannot be so sure about it. And point P is on a radial plane, which is obviously closer to x-axis, 30 degrees, and point Q is on a radial plane, which is a door which is open more wider as compared to point Q. So these are the you know, some example coordinates which I just took, but generally we can see that point P is on has got the coordinates r1 theta 1 phi 1, q r2 point Q has got coordinates r2 theta 2 phi 2, and the relationship is given as usual, that the R2 is nothing but slight increment in the radius of the inner sphere. Theta 2 is slight increment in the angle of the inner cone or the narrower cone, and phi 2 is nothing but slight increment in the opening of the radial plane or the angle of the radial plane with respect to x-axis. Okay, all right, Janab. Obviously, but remember that these coordinates which the difference, that is if you take for example dr 5 minus 3, it will be 2. For example, we are using the units of meters. 2 meters does not qualify as the differential change in the radius, because it is a very huge macroscopic change. 2 meters or 2 centimeters or even 2 millimeters difference is a huge difference, and that difference does not qualify to be regarded as dr. So you should not be taking this dr as 5 minus 3, okay, or this theta 2 or this d theta as theta 2 minus theta 1. Yes, d theta is theta 2 minus theta 1, but the difference between theta 2 and theta 1 is minuscule. It is extremely small, that can be regarded as insignificant practically, but in this case, if you see that the change in theta is 70 minus 50, this is a huge 20 degrees change, which does not qualify as to be regarded as differential change in theta. Same is the case with this phi. But in order to show you that how the differential volume would look like, I've taken these, you know, big macroscopic changes, but the differential volume will be infinitely small, you know, a dot version of the same exact shape. So that should be clear, or not only in the study of a spherical coordinate system, but also in the study of cylindrical and rectangular coordinate systems. This point should be clear. Okay, so now we are going to discuss differential volume. For that, we should know the sides of this, the shape first, the shape of that differential volume, and then after that the length of each side, so that we can find the differential volume, and then differential surfaces, and at the end the differential length. All right, so this we are standing at point P, this black dot, and now we are moving. Now we should know that if I join this point to origin, what I will get radius r1. I am not writing it here for the sake of clarity, but you should know this. But however, I would definitely like to write that this is theta 1. I hope you would be able to see it, but this is theta 1. Okay, now from here I would say, as I did in the case of cylindrical coordinate system, from here move in the direction of AR. How many units? This differential unit. this differential units, okay, negligibly, okay, but I cannot move here negligibly, rather I would move here considerably so that you can appreciate what we are doing. So I am using this blue marker, and I hope you would be able to see that blue marker, okay. This is something like, this would be something like, you know, this. All right, this blue line is nothing but differential movement in the direction of a theta. How much? A very small distance. So now this should be clear that the length of this blue line, I hope you would see it blue, if not, but then I'm telling you this is the blue line. The length should be dr, the differential length dr, okay. Now I have reached this to this point, okay. Now since I have moved along the radial line just like this, along this blue line, when I moved, okay, I was moving in the direction of AR, and this radial line is nothing but intersection of theta equals to constant cone and phi equals to constant cone. It means that moving along this radial line only changes the value of r, and it does not change the value of theta or phi. So if I have moved from here to here along this radial line, I have only the point where I have reached the new point. This point would lie on the same radial plane, that this point would lie on the same radial plane, which would actually make angle phi 1 with respect to x-axis, okay. And also it would lie on the same cone which is making an angle, you know, theta 1 with respect to z-axis. So obviously this is this extension of the same line, okay. So now if I had dropped from this initial point, if I had dropped a perpendicular, you know, a perpendicular on the xy plane, so that would strike the xy plane at a point, and if I would join that point to origin by a straight line, that straight line would make an angle phi 1 with respect to x-axis. This is all you know. So if I would drop a vertical from this new point, it would land on the same radial plane. So nothing new about it. All right, after reaching this point, only I'm on the newer sphere, a larger sphere, but on the same cone and on the same radial plane. Now if now I would say that move in the direction of a theta. So moving in the direction of a theta means that the value of r and the value of phi should remain the same. It should not change at all. Moving in the direction of a theta means moving along this red line, which was tangent to this orange curve, and this orange curve was made by the intersection of phi equals to constant and r equals to constant surfaces, okay. So along this curve, moving along this curve would not change the value of r, neither would it change the value of phi. Along this curve, what will change? We will get the change in the values of theta only. It means that we have to move tangentially with respect to the surface of the sphere, or tangentially along this circle. Moving tangentially throughout along this circle means that I am moving tangentially on the surface and I should do that because the values of r should never be changed, only the values of theta should be changed. All right, and moving along this surface also means that I am moving along tangentially along the surface, also means that I am also simultaneously on the same phi equals to phi 1 plane. Okay, so now I am using this red marker to move along you know, keeping this radius same, and now I'm moving along tangent. Should I draw it or should I not? Okay, so now you can imagine that I am just moving it, keeping the length constant. I am just moving it down towards the z equals to 0 plane, maintaining this is curve. You might see it, you know, a straight line, but this is actually a curvy surface, not a straight line, right? Okay, so now reaching here, if I would join this point to origin, what I'll get R2, okay, because I was on the larger sphere. Keeping that surface, keeping on that surface, I just changed the angle. So if I just join this line from here to origin, okay, from here to origin, meaning that I am on the outer sphere, then I'll come on the inner sphere, then from inner sphere I'll go all the way to the origin. So you know, I did not draw that portion which is between the inner sphere and the outer sphere, because I want to color code it, that the transition between the inner sphere and the outer sphere should be given by, you know, this blue color, so that we can better, you know, visualize it. Okay, so now this difference in angle between these two lines, I'm not going to show it here, but this is d theta. This is d theta. Okay, now I have reached a new point here, and from here I want to move now in the direction of a phi. How many units? I want to move d phi units, meaning that I just want to open the door a little bit wider. Okay, so now you should know that moving in the direction of a phi means that only values of phi should change. These two should be constant. So it means that I should move along the intersection of these two fundamental surfaces. So r equals to constant, theta equals to constant, gives us this yellow, you know, latitudinal curves. So moving along the latitudinal curves will give me, or if we see it from the top, this yellow curve. Okay, this yellow circle. So keeping the radius constant and moving along, you know, the latitudinal curve, meaning that tangent to this yellow circle, or tangent to this yellow circle that you are seeing here, meaning that I should remain, you know, I've drawn it with green. I hope you would see it in green. If not, then never mind, the other one final picture is green. So now I have reached not only a new wider cone, not only a new surface, spherical surface, but also a new radial plane. So now if I would drop, when I was here, if I would drop this perpendicular on z equals 0 plane, I would reach on the same phi equals to phi 1. But at this new point, after moving in the direction of a phi, how many units? D phi units. If I drop a perpendicular, I would land on a different point, and if I join this different point with origin, okay, so now this new line is making an angle phi 2 with respect to x-axis. Okay, all right, dear. So now here we are now at the new point Q. So now just to give you the picture, actually this point P is formed by r equals to 3, theta equals to 50 degrees, and phi equals to 30 degrees, 3 fundamental surfaces, and point Q is formed by r equals to 3, theta equals to 70 degrees, and phi equals to 60 degrees, similar surfaces but with different angles and dimensions. Okay, and remember that only this sphere is constant, is finite. All the other surfaces like theta equals to constant is an infinite cone having infinite height, and phi equals to constant is a radial plane of infinite height and infinite width. So it means that out of the 6 fundamental surfaces which are forming these 2 points, and all those fundamental surfaces are different, okay, having different dimensions. Out of those 6 fundamental surfaces, 4 are infinite, that is theta equals to 50 degrees and theta is equals to 70 degrees, 2 infinite cones, phi is equals to 30 degrees, phi is equals to 60 degrees, 2 infinite radial planes. But these 2 finite spheres and 4 infinite surfaces combined together, they are enclosing a finite volume, and we are trying to find out that volume. Okay, so how to find out that volume? Again, if I just draw a curve between a curve on the outer sphere, okay, between theta equals to theta 1 and theta equals to theta 2 cones, what I would get, I would get this curve, okay. And if I draw again a curve which starts from the narrower cone towards the wider cone while I am on the inner sphere, and while I am on the phi equals to 30 plane, radial plane, that would be something like this. And if I draw again the change which happened while moving along the inner sphere and on the phi equals to 60 radial plane, and only changing the phi, what I will get, I'll get this curve. Okay. Similarly, if I would try to find out the change which happened on the outer sphere between these 2 points, okay, that change is nothing but the change in the values of radial plane, okay, because moving from this point to that point in tangential direction, it means that I am moving along these yellow these yellow latitudinal lines. Okay, if I would complete the circle, I will get a, if I would keep on going, I will get a circle, but I am not interested in that. Okay. Similarly, if on the inner sphere r equals to 3 sphere, if I want to move from this point to that point, okay, the point at the background, the only thing which is changing, meaning this point is also on theta is equals to theta 1 cone, this point is also on theta is equals to theta 1 cone, this point is also on r is equals to r1 sphere, this point is also on r is equals to r1 sphere. So if I am moving along this from this point to that point, the only thing which will change is phi. Okay, phi. So another latitudinal curve, but that latitudinal curve is on the inner sphere. Okay. So similarly for the, if I want to move from this point to that point, I'll have to follow along a latitudinal curve. Okay. So how about moving from this point to this point? The only change which I am getting is in the direction of AR, or the radius is changing. So since this is on the background, so I'm just making it a dotted line. Okay, dotted line. And similarly between this point and that point, I will get change in radius only. Okay. So now if I just remove all these, extra lines, the final shape which I'll get is this one. And differential volume, whose formula which we are trying to find out, is nothing but exact replica of this shape, but at the differential scale, that is extremely small scale. Okay. So the length of this line has been decided. This is dr. The length of this arc, the red arcs or this arc, can be defined, because we had already discussed that. Now I think I can draw it here. This black line, which is passing through point P, this was point P, and this was point Q. So this line, which then turned into the blue line, okay, this is making angle theta 1, and then we move from here to here, okay, and then join this point to origin. So we got this line. The difference between these two lines is nothing but d theta. This is d theta. So the length of this line, or length of the distance between this point and origin, is given by r, and the angle between this point and that point is d theta. Okay, this point or that point, or this point or that point, angle difference is d theta. So obviously the the length of the arc length is nothing but r d theta. Okay, and the arc length green curve, or the inner green curves, can be easily plotted over here, because we know that these green curves are nothing but on the curves on the latitudinal curves. So this yellow line is latitudinal curve, we all know this. So if I'm moving from this point to that point, the only thing which is being changed is d phi. Okay, whether I move from this point to that point, or this point to this point, or this point to this point, or this point to this point, the only variation in angle, the only variation is in the azimuthal angle, which is quantified by d phi. So let's say now I'm just messing up with this diagram. Let's say if you see it from the top, okay, this is point P, okay, and let's say this is point Q. Point Q is here, okay. So now this is point P and point Q, and okay, this should make angle phi 1 with respect to x-axis, and this point should make, this line should make angle, you know, phi 2 with respect to x-axis, and the difference between the two is nothing but d phi. Okay, so all right, so this is on the latitudinal curve. Okay, so the arc length of this yellow, let me write the arc length here, is given by radius multiplied by the angle difference, and angle difference is d phi. So radius we had discussed in the last class, it is r sine theta, and the angle difference is d phi. So I can say that the arc length of these green curves is r sine theta d phi. So now we have got all the three curves, formula for all the three curves. So Janab, differential volume is nothing but this side multiplied by this side multiplied by this side. So this side is r d theta, and this side is r sine d phi. So again, r means r square sine theta d phi. Okay, earlier r d theta, then r sine theta d phi, and then this length which is nothing but dr. So write it here, dr. So let me write it with wider fonts, larger fonts, so that you can see it. dr d theta d phi, r square sine theta dr d theta d phi. It is customary to write all the variables of r first, then theta, and then phi, then differential of r first, then differential of theta, then differential of phi. So this is differential volume. So now the surface over which r is constant, that is this patch on the outer sphere, or this patch on the inner sphere, the patch which is formed by these two green lines and these two yellow lines or curves, okay, on the outer patch or inner patch, although the size or area of the patch is different, but formula would be the same. Over this patch and this patch, formula would be the same, although the size would be different. Okay, because this smaller patch is on the inner sphere, the larger patch is on the outer sphere, so never mind, the formula for this, each of the corresponding side is the same. So the formula for area, surface area, would be the same. We know that the surface area is nothing but vector quantity, so we will just multiply this one side, which is r sine theta, one side is r sine theta, and the other side is r d theta. So if we multiply these together, what I'll get, r square sine theta, r square sine theta d theta d phi. There should not be any dr, because we are saying that over this differential length r is constant, so there is no concept of change in r. And we know that the direction which is perpendicular to this patch would be ar. We should now know this. Now the surface over which theta is constant would be the one which is formed by these blue lines and these green curves. These green curves are on, this smaller green curve is on the inner sphere, this is on the outer sphere. This blue line is on phi equals to phi 1 plane, and this blue line which is on the background, this is on phi equals to phi 2 plane, or the larger plane, okay, a wider open plane with respect to x-axis. So the formula for this is again r sine theta d phi multiplied by this length of blue line, which is dr. So as I said, it is customary to write entities with respect to r first, then theta, then phi. So now you can see that there is no d theta here, because we are saying that we are writing the formula for the patch or the surface over which theta is constant, so there should not be any change in theta. Okay, so this is also a vector quantity, so we should multiply it by a unit vector a theta, and y you should now know. Similarly for ds, where phi is constant, which is made by the blue lines and these yellow curves. Okay, so blue line is the yellow curve is r d theta, and this blue line is dr, r dr d theta, and unit vector a phi. Note that there is no d phi here, so we have got the differential volume, the differential surfaces, and now differential length is what? The address to reach this point with respect to this point. So what would that be? That would be if we are already on point P, move in the direction of AR, how many units? dr units. Then move in the direction of A theta, how many units? r d theta units. Then move in the direction of phi, how many units? r sine theta d phi units. In the direction of phi, move in the direction of r dr units, move in the direction of phi theta r d theta units, then move in the direction of phi, how many units? r sine theta d phi units. This is now differential length, and it should be again a vector quantity. Okay, so now this is it for spherical coordinate system. Now once again, if we want to convert the coordinates given in the spherical coordinate system to and from Cartesian coordinate system, what should be the strategy? We should also look into that. Alright, so now if I'm at this point, I can give the coordinates of this point in terms of Cartesian coordinate system or in terms of a spherical coordinate system. So if the coordinates are already given in a spherical coordinate system, that it means that r, theta and phi is already known, meaning that the distance of this point from origin is known, which is r. This is r, and if I drop a perpendicular from this point down to the z equals to 0 plane, what I'll get, and if I'll get a point, and if I just join this point to origin, what I will get the line which is making an angle phi with respect to x-axis, and this height is nothing but z. Okay, and the angle which this line is making with respect to z-axis, this is theta. This is how we reach this point P in spherical coordinate system. So if I just find out this height, I'll get z. Okay, and if I just drop this point is on z equals to 0 plane. If I just drop a perpendicular on x-axis and on y-axis, so this length is nothing but equals to this length, and which is x, and this length is y. So if I would somehow find these lengths, I would be able to reach this point using Cartesian coordinate system, and that is pretty straightforward. Now, why straightforward? We know that this line, the length of this line is what? The length of this line is r sine theta. Okay, the length of this line is r sine theta, because if I just draw the same parallel line here, okay, this line will be nothing but the radius of the latitudinal lines. Okay, all right, so this is r sine theta. Okay, so if this line is r sine theta, so x should be r sine theta cos phi, r sine theta cos phi, and y should be r sine theta hypotenuse, r sine theta sine phi, r sine theta sine phi. Okay, and how about this height z? This height z is nothing but this height, okay, this height. So this angle is theta, and this length is already r, we know that. So this height, or this height, because these are alternate angles, this is theta, this is theta, this is theta. So if this is r, so this height is what? R cos theta. Or in other words, if we were given x, y, and z, we can find, this distance, or the r. We can go the other way also, that if the point is given in terms of x, y, and z, we can find r, theta, and phi. So if this x is given to us, this length is given to us, this height is given to us, so we can find the length of this r, the distance between these 2 points, using the distance formula, under root x square y square z square. You can see that these x, y, and z are nothing but the x, y, z projections of this this line, whose length is r. Okay, and if you want to find theta, you can just take theta is equals to cos inverse of z upon r, and r is just, we found out it is to be this, so cos inverse z upon under root x square plus y square plus z square. And phi, since we have got the, this is the phi, tangent inverse of y upon x, same as previously. All right, so this concludes the topic of spherical coordinate system and how to convert a point from cylindrical to spherical coordinate system. I hope this discussion would have been really helpful to you, and from next week inshallah we will start the electrostatics, and I would assume that by that time you would have completed all the end of chapter problems as well as the drill problems, which I have already shared with you on the Google Classroom platform. So with this I would like to end this lecture, and I would finally again urge you all to comprehend all these mathematics with practice, and these concepts should be, all the concepts which we have discussed in chapter number 1, they must be they should be and they must be on your fingertips. Okay, so that we will just keep referring to these facts, and while we will study the physics or the electrostatics, the electromagnetics, inshallah. So we will just keep referring back to these facts, and at that time we won't have time to explain each and everything. We have already spent quite a lot on discussing the language of electromagnetics. Okay, with this, good luck and see you in the next class. Assalamu alaikum.